everyone. My name is Catherine, and today I'll be talking about the Simulink exoskeleton modeling for my advanced mechatronics project. So today we'll be talking about the hip exoskeleton modeling. There are 3 tasks to this project. So for the first task, I'm going to first introduce the human exoskeleton coupled model, and then derive the transfer function of the bandwidth and the backdrivability of the exoskeleton model. So for task 2, I'll be comparing 2 electronic actuation paradigms of exoskeletons. And the 2 actuators are the quasi-direct drive actuator and also the series elastic actuator, and both of which are very common in modern robotics. And the third task, I will be showing the Simulink model of the bandwidth of the system and also the Simulink model for the backdrivability of the system. And using the given parameters, I will show you the results I got for the Simulink simulations for both the bandwidth and the backdrivability for the 2, the quasi-direct drive actuator and the series elastic actuator. So first of all, I'm going to introduce the human exoskeleton coupled model. The model for the transfer function involves the electrical part of the system and the mechanical part of the system and the transmission and variable structure. So before talking about transfer functions, I want to talk a little bit about the bandwidth and backdrivability. So bandwidth is the key specification in both analog and digital systems. The bandwidth captures the frequency of input before the system response drops to 3 decibel from the DC gain. So basically, it is how quickly I can change an input signal before the system cannot capture our the frequency anymore. And for backdrivability, it is a special case of force control. So it is like the level of easiness, like how much force we need to apply to the gears in order to move the gear in the reverse direction. If the backdrivability is too low, we would have used more metabolism energy onto the device, which is something that we do not want for the exoskeleton system. So for the transfer function, as we have previously talked about, for this bandwidth transfer function, there is the torque input and the torque output from the left to right. And the whole block diagram involves the motor mechanism, the electrical component of the system, and the gears, and also the variable structure of the system. To derive the transfer function, first of all, we will need to simplify the block diagram. And in this field circle, in this area, we're going to simplify this whole block as G of S, which is the torque output over the voltage input. And this is the equation I got from deriving the blocks for the transfer function. So after getting G of S, we can simplify this area. And we can redraw the block diagram over here. So to get the bandwidth, which is the output torque over the input torque, we just have to use the output torque T of A divided by T of R. And finally, we get the bandwidth in this equation here. And next, I'm going to talk about the backdrivability of the transfer function. The backdrivability of the transfer function is very similar to the bandwidth transfer function. But the only difference is that we do not need to apply torque to the system because we're testing how much force we can apply to the gears. So the input voltage over here is going to be 0. And there is an output voltage and as well as input position, angular position as our hip rotates. So if we want to get the backdrivability of the transfer function, we will need to get G of S as the output torque divided by the angular position of the structure. And this is the equation we got for the backdrivability. And now I want to compare the difference between the quasi-direct drive and series elastic actuator. For us, as we're developing the hip exoskeleton model, we want to save as much metabolic energy for the user as possible, and also we want to provide as much torque as possible for the structure of the drive. The quasi-direct drive is a large torque motor and also a small gear ratio. And the back drivability and the bandwidth are high in quasi-direct drive, and the mass of the weight of the quasi-direct drive is lower than series elastic actuator. For the series elastic actuator, there's a small torque motor, and it has a large gear ratio, and it also has a spring that we need to consider. And for series elastic actuators, the back drivability is relatively lower compared to other actuators, and the bandwidth of the actuator is also lower. Quasi-direct drive actuator will be the preferred actuator to use. These are the parameters that was given for the simulation on Simulink. So this is the Simulink model for the back drivability of which can be applied to both motors. Code that we input into MATLAB to run the Simulink model. And as you can see here, for motor electrics, at the input is 0 because, as we previously talked about in the transfer function, that we do not need a voltage input for this function. And here is the output of the model. So after running the model, we can see the two different actuators. The gray one is the series elastic actuator, and the black curve is the quasi-direct drive actuator. From this graph, for resistive torque and time, so the quasi-direct drive produce a lot less resistive torque compared to the series elastic actuator at the same position. At time of about 5 seconds, the resistive torque in the series elastic actuator is about 12.11, but in the quasi-direct drive actuator is only about 4.827, meaning that the back drivability in the quasi-direct drive actuator is proven to be higher than the series elastic actuator. For the bandwidth of the Simulink model, the components are basically the same as the back drivability model, other than the input torque we have to put here. The result that we got from the Bode diagram, as we can see here, for the quasi-direct drive, for the quasi-direct drive Bode diagram, at -3 decibel, the frequency is about 221.3 hertz. And at the same -3 decibels for a series elastic actuator, the frequency is only about 14.7 hertz. That means that if we go over 14.7 hertz for the series elastic actuator, the system will not be able to accurately detect the frequency input anymore, which has proved that the quasi-direct drive actuator has a lot higher bandwidth than the series elastic actuator. And finally, I looked at the output torque of both the quasi-direct drive actuator and the series elastic actuator at the time frame of 30 seconds. So as we can see here, that the torque, the system has accurately detected the frequency of the torque input. The frequency gets higher and higher over here. So at about 20 seconds, the system started to attenuate, and it can no longer accurately predict the input frequency anymore. But at a series elastic actuator, at about 4 to 5 seconds, the system already started to attenuate, meaning that it cannot accurately detect the input signal anymore. So this result has proven that the quasi-direct drive actuator is a better actuator to use for the exoskeleton system. But the only downside of quasi-direct drive actuator is that it cannot produce as much assistive torque that's needed for an exoskeleton. system.